Hello and welcome to the lecture Transformer Part 2. In this lecture, we are going to understand the transformer architecture. Firstly, we discuss the encoder architecture, the input embedding, positional encoding, multi-rate attenuation being discussed. Then we'll understand layer normalization, feed-forward neural network under this encoder architecture. Then we'll discuss decoder architecture, basically the masked self-attenuation discussed. In recent time, transformer is one of the most popular generative model, especially for sequential modeling in natural language processing and any other application, even in vision application. So a transformer is a deep learning architecture designed for processing sequential data, especially as I said, it's NLP problems. It was introduced or proposed by Arijit Sur et al. In 2017 in a seminal paper, Attention is All You Need. Now, what the major aspect of the transformer that is different than the contemporary models or CNN-like models, that it uses self-attention. As we have seen in the recurrent neural network, the RNN, LSTMs, etc., they use context or somewhat attention also. Here, the transformer uses another typical attention, it's called self-attention, which allows the model to focus on different parts of the input sequence simultaneously and thus capture the long-range dependency efficiently. And that is one of the reasons that make the transformer very popular or very efficient, specifically for the sequential modeling and mostly in natural language processing tasks. Now here you can see that the main figure taken from the paper of Arijit Sur and NIPS 2017. Transformer is a encoder decoder. The full transformer is encoder as well as decoder. And before going to encoder, the inputs are, there is the input embedding, that may be what to vague and any other embedding. Then there is a positional encoding, that a position of the word in a sentence like this. Then it comes to the actual encoder. Then there is a few things that multi-head attention. Then we have to addition and normalization, feed-forward networks, residual connection, and so on. So many things there. We will discuss one by one. Similarly, in the decoder side also, there is a output embedding. It is input, outputs are coming as input. So positional encoding is also required. After that, the main decoder, that masked multi-head attention, that also we will discuss, and normalization layer. And there is another extra layer, that is multi-head attention, it is coming from the encoder input. And then several this add normalization, feed forward, again add normalization layer. So this is the typical transformer decoder. We'll see one by one what is the requirement of these layers and why this is used. Then is that there's linear fully connected layer and softmax we get the output properties. So this is a very overall looks that how this transformer in architecture, encoder as well as decoder architecture is. Now one special advantage of transformer, that it processes data in parallel rather than sequentially, which make the transformer much faster to train and scales well to large data set. So transformer is basically faster than these recurrent models like RNN steps. And definitely this formulation or this foundation of transformer is a core architecture of many well-known models like GPT, BERT, etc. that are now very, very famous in the literature. Now, how the transformer is different than the convolutional neural network? This question is that we always try to understand why transformer is somewhat replacing CNN, mainly for sequential or sometimes for mission task also. So it differs from CNN mainly in how it processes the input data and capture relationship. That we have to understand how it. So CNN use the conventional filter, that convolutional filters, and scan small local regions because the effective field of these convolution kernels is local in an image. So these small local regions of the input to detect the patterns such as edges, textures, making them highly effective image processing task. On the other hand, or in contrast, transformer rely on self-attention mechanism, which allows the model to consider the relationship between all elements in their input simultaneously. So that is one of the major differences here, that it is based on the local, where transformer is basically try to find out if there is a sentence or there is a series of image patches. What transformer want to do, it try to find out the relation between each patch to each patch, each word to each word. So that relationship, or can say long-term relationship, is much easier to model for the transformer. So this enables this kind of self-attention based modeling transfer to capture long-range dependency, because it basically try to find out the relation between different patches or different words in a sentence and process sequence in parallel. Whereas CNN is primarily focused on local spatial features and then build global understanding through the many stacked layers. It also tried to find the global understanding or global statistics, but through the stacked layer. Okay. As a result, transformers are widely used in natural language processing tasks like BERT model, GPT model, while CNN remain dominant in traditional computer vision tasks. But in recent times also we say that the ambition transformer and VITs are also very popular. Okay. Now we are going to understand the transformer architecture. As we know, the transformer has two basic modules. One is encoder module and another is decoder module. We take an example of neural machine translation, where a sentence in a particular language is being translated to another language. Here we have chosen a Hindi to English translation. Now मैं एक छात्र हूँ, that is input to this transformer, and then it is translated to this English, the corresponding English statement. Now we are going to understand this encoder and decoder. Now one thing is worth mentioning here, that all the transformer based model are not consist of both encoder and decoder. Some models definitely have both encoder and decoder like this. Sometimes it only use encoder. It's called encoder only model. Sometimes it's use only decoder. It's called decoder only model, and so on. So let me try to find out what is the basic structure of this transformer architecture. Now here you can see that this is the transformer architecture. This is a series of encoder followed by a series of decoder. Okay. Now this 6 is a very hypothetical number. It may be less, may be high, depending on the application. This sentence, after text embedding and positional encoding, these things done, fed into encoder, and this output of this encoder go to the next encoder and so on. In this way, it will, the last encoder produce the context information like attention something that is going to the decoder, and this all the decoder this information is coming, and this decoder output to this, so on. Finally, the final decoder give the output. So this is the basic understanding of this transformer. Now first we'll start with encoder. So encoder is basically this kind of node. So what are the basic building blocks of the encoder? Before feeding to the encoder, this statement, this in Hindi, this sentence, that these words, first word embedding is done, then the positional encoding will come one by one, then it's ready to input to the encoder. And in encoder there is a few, it is called multi-area attention, that we see. Then add and normalize, that is done. Normalize means layer normalization, and then this is fed to the feed forward network. This is basically a multi-layer perceptron, and then again you can see some addition and layer normalization. Finally we get the output from this particular encoder layer, and it is go to the next encoder layer. So this is the basic of the full encoder. Okay, so first what we'll start with, that this is the basic diagram of the particular transformer model, both encoder and decoder, and one encoder basically expand, and this is the encoder structure that we have, what we have discussed. Now first we start from here and we'll see how this will by this particular encoder layer. Now we start with a sentence, that this is a Hindi sentence, मैं एक छात्र. So the first step is that input embedding. So what do you mean by input embedding? So here input embedding means that it may be generally a text embedding or a text. So input embedding in a transformer is a process of converting words or tokens in a sentence into numeral vectors or numerical vectors, so that the model can understand and process it mathematically. So basically this is an input. This is a kind of text embedding. If we take an example of sentence and make these tokens, or you can see in a sentence we can have different kind of tokens, that's words, subwords, something like that. Okay, and so this token, corresponding token, is converting to a particular numeral values or numeric values. So in a transformer, the input text is first tokenized into smaller units, words or subwords. Then each token is then mapped or transformed into a dense vector representation called an embedding, using an embedding matrix. So we can say the popular embedding is what to take embedding or something like that. So these embeddings capture the semantic information about the words. That means that words with the similar meanings tend to have similar vector representation. So in this kind of input embedding, for this kind of examples, since it is a sentence, that we first split it out to this token, and each token, that means each word, is converted to some numeric value, and so that this dense vector representation can be used to capture the semantic information about the words. Okay, so that is called the input embedding. Now we will take an example that this Ron is a good boy. Now it's fed to the tokenizer and it split the individual words, or these words is now token. So Ron is a good boy. So these are the words and token. Then go into the embedding layer and we get this some values here. So here you can say that it is a 512 dimensional vector that is being given to a given token or a particular word. So this is also another 512. So input embedding is basically given this sentence the corresponding these values. Okay. Now come the positional encoding, the next module. So what is the positional encoding? That the positional encoding is a technique that used to provide the information about the order of the words in the sequence. Now here you can see that there is a Ron is a good boy. And when we do this kind of, it is a word by word. That embedding doesn't hold the information, doesn't contain the information that the sequential position or some positional information of the words or a token within a sentence. But for a sentence, a meaningful sentence, this positional understanding is very important. So we do what we do in this positional encoding. Since transformer process all the tokens in parallel and do not inherently understand the sequence order, positional encoding is added to the text embedding so that model knows the position of each token in the sentence. And that is one of the major thing that is required and with this text embedding. So in this method, a unique vector representation of position or position aware vector representation of each token is generated and added to the token embedding before it enters to the transformer layers or encoder layers. Let's see how. So these positional vectors are typically computed using the sine and cosine function of the different frequencies, allowing the model to learn the relationship between the position in the sequence. That we will see in the next slide, that how actually it is. So what basically we do by combining these token embeddings with positional encoding, the model can distinguish between sentence like dog bites man or man bites dog. Okay, so now these things. Look, the sentence in this particular sentence, the words are same, but since their positions are different, the meanings are completely different. Where the word ordering changes the meaning. So this positional information is then used by mechanisms such as self-attention to capture the contextual relationship between the tokens. So that's why position encoding is a very important module before into the actual encoder. So here is basically this information of each word in the input sentence and relative distance closer between the words in the sentence. Now Ron is a good boy. This is close to Ron, but boy is relatively distant. So here you can say the vector size is 12, and there is some positional information, and we can add it to get the position or this embedding. So this is basically the positional embedding or positional encoding. Now here you can see that we concatenate special positional coding J to this text. Use the function POS that basically that this d-dimensional real values process the position J of the vector into the dimensional space. So this P. So it is a lookup table based approach. Parameters to use the post T at epsilon 0 to T. Lookup table contains T into T parameters. And generally P of T is sin W T cos omega 1 dot T omega sin omega 2 T cos omega 2 T and so on. Where this omega is 1 by T. So these are the basic table architecture from where we get the positions or positional information of the words or tokens within a sentence. Now we go to the encoder of this transformer. So here the first module is multi-head attention. And what we mean by multi-head? We already discussed in detail what is multi-head attention in previous lecture. Now from the architectural viewpoint we try to understand a similar concept or the same concept. Now here we have this sentence. Now we do this word embeddings. Then we do the positional encoding. And now we are ready for the encoder. Now here we assume one thing, that for our simple understanding, that each this dimension of these vectors, these embedding vectors, which is basically the word embedding as well as positional encoding, two things, is a 1 by 4 dimension. And there is this is just a very hypothetical example. So that is some WQ matrix, WV matrix and WK matrix corresponding the query vector, the key vector and the value. So it is a query matrix, or it is a value matrix, or it is a key matrix. Now for all these words or the tokens are basically multiplied with this in this. It's a fully connected. So Qi, that means Q1, is basically this multiplied this. So it is basically 1 by 4 to 4. So it is a 1 by 4 into 4 into 4, it is a 1 by 4. So such 4 things will come because there is a 4 words in this particular sentence. So there is a kind of 4 words. The values. If we concatenate it, we can again a 4 by 4 matrix. So this is our matrix. So similar as the value matrix, this is the value parameters, this parameter matrix. When you multiply with this with x, we get this value matrix. And if we can adjoin, we can get a matrix like this, a V matrix. And similar for the K matrix. Now, as we have discussed in details that how we are going to find out the alignment score, that was basically K to K transpose. And we if use the scaled, basically this is the kind of dot product. Now it is the scaled dot product. This is Q KT into what? D of K. What is the D of K? Is basically the input dimension. Now we put this value in the softmax to get this softmax code. Okay, and this softmax code, if we multiply with V, that we can get the this self-attention that we already have seen in our previous discussion. So ultimately this softmax of Q into the by D of K this way. This is the self-attention. But one thing is important, this is self-attention, is not the multi-head attention. Now we'll see what is multi-head attention. It's based on these only. Now here we have changed the different dimension. It was very easy to, we have to in this matrix draw this. Now we can understand this is, so now more realistic example, we change this dimension so that you can understand properly, because now we understand everything. Now we can very easily do this. Now here also this input is now 6 words and each words that have 512 dimension. So the input embedding plus positional encoding. So one word is 512 dimension, 1 to 512 dimension, and such 6 words are there. And this is into Q, that what we get this Q matrix. Now with K in WK. In WK now 512. Initially it was, the last example it was 4 cross 4. That just dimension we have just changed. As now it's 512 by 512. So corresponding K matrix is 6 into 5. And it is 512 by 5 matrix and get that. Now what we basically do? Just recall our understanding that what we have done in case of multi-head attention. We split the different heads. So it is some kind of this, that 4 heads we have used here. Okay, these 4 heads. So Q1, Q2, Q3, Q4, 4 heads. K1, K2, K3, K4, these 4 heads. P2, P3, P4. And in this fit, since it is a 512, so 1 is so 128 dimension. 6 such things are there. 6 such 120 dimension Q vector and 6 such 120 vector. So all these have this dimension. Now from these matrices can get, if we are joining these 3, the first self attention, this head 1, and this is a head 2, again self attention. Now you can say multiple heads. What essentially it do, as we discussed, you may recall that 2 different words in a sentence, there is multiple 6 words. Now take any 2 words and try to find out the contextual relationship. So such 4 pair, if you say, of words we take, and in this particular hypothetical example, that 4 pairs of 4 heads we are counting, and for every pair we get the self attention, and such 4 pairs or 4 heads are there, so we get the. So it will give increase the flexibility or expressiveness of the model much higher. So it's 4 times basically. These 4 heads rather than 1 self attention, we have now 4 self attention between 4 pairs. So this is the multi-head attention, and that we have used here, this multi-head attention. So next come the layer normalization. See that these layers is normalized. This layer normalization is basically used so that we make it more robust. We'll see what exactly in some later slide, what exactly the role of layer normalization. Then come feed forward neural network, and then again this add a normalized layer normalization, and finally we get this output that is ready for the next encoder layer. So as a whole, this is the encoder of this full class. Now we are going to discuss the transformer decoder. As we seen in this main diagram, this decoder has basically almost similar architecture, but there is few things So one is masked multi-hit attenuation, and there is one connection is coming. So here this is the decoder architecture, that there is n number of decoders are there, and this input is coming here, and this is got the output. Now one thing that we have noticed earlier also in this kind of task of neural machine translation, that the first input is basically start and first output is I. Now this first output is coming here as input to the second node. Second output is coming the third input to the third node, and so on. So this is in that sense an autoaggressive thing is kind of thing. So in this kind of example, this is a very common thing. And in transformer also it is being used. Now what is important, that within a decoder what is the architecture is. So this whatever this, that we will see one by one. Now here you can see that this decoder 1 is been expanded here. Now in this expanded view, we'll say first this, so it is coming from here, and next to the Y0 that is coming to the next layer, next decoder layer. And here is this encoder, the context coming from the encoder coming. Now here first is positional encoding, and that is very similar in the encoder. Then we use the masked multi-hit self-attenuation. What do we mean masked multi-hit self-attenuation? That discussed earlier, the whatever the positions being already been done or been outputted, that is only visible to that current node. The future nodes are not available. So that part, the future parts are masked. Okay. So this is called masked multi-hit self-attenuation. Self-attenuation is basically computed with this masked. Then comes the normalization, and then again the multi-hit attenuation. Now we don't use the self-attenuation because this is not self-attenuation, because there is a two input. This is from here, this is the query input, and this is the context. Then the corresponding similar thing is layer normalization, then NLP is the feed forward network, and then again layer. So it's more or less same encoder. Finally, we got fully connected layer. So this fully connected layer is basically after this. So these are the basic structure. So the thing we try to discuss that. So a decoder block in the transformer takes two inputs, a set of input vector x from the previous decoder and a set of context vector c from the encoder. That we can see, that is in the previous input it will come in. So this from here to here, here to here, and so on. And this is a context vector from the encoder thing. So from the encoder thing. Okay. So then it produces a set of output vectors y used to generating the next tokens in the sequence. So here you can see that with that go to this they generate tokens that go to the next decoder and so on. The first component is masked self-attenuation. What does this mean? As we said, that where each position in the sequence can only attend to the previous position or past inputs, not the future ones, ensuring the correct sequence generation, and that is called the masked self-attenuation. That is here. Then after this, a multi-hit attenuation layer attends to the encoder outputs. This layer is not self-attenuation because it uses the encoder context C. As we see, it is not self-attenuation. As we said, this is C and this is Q. Okay. C and key and values, and this allows this decoder to focus on the in parts of the input sequence process. Finally, a feed-forward network processes the result. as we see that this feed forward MLP. When we have linear normalization, we get this. After that, we fully connected to get these tokens. Okay, so this architecture is highly scalable and parallelizable, and which makes the training efficient, but it can require high memory usage, because you can see that there is a lot of process with this, the attention operation over the large sequence. So this is the transformer decoder. Now we see there is some layer normalization in both encoder and decoder. What is basically layer normalization do? So layer normalization is an important component in the transformer architecture. It is used to stabilize and speed up the training of the deep neural network, because there is a lot of coefficients are there, so we have to the layer normalization. Another reason for using layer normalization is to improve the gradient flow in the decoders. That is important. Next is the residual connection. A residual connection in transformer is used to improve the training of the deep neural networks by allowing the information to bypass certain layers and flow directly to the later layers. That's the concept in ResNet, kind of similar concept. In a transformer block, each sublayer, such as multi-head attention or a feed-forward network, has a residual connection, but the input of the sublayer is added to this output. That will sometimes help to prevent the vanishing. The residual connection are typically followed by the layer normalization, which stabilizes the activation. The main purpose of residual connection is to prevent the vanishing gradient problem, make training deep architecture easier, and allow the gradient to flow more effectively during propagation. As a result, they enable transformer to stack many layers while maintaining the stability. So residual connection is one of the features. Finally, there is a feed-forward neural network. So this feed-forward network is something like MLP, like this multi-layer perceptron, fully connected network applied to each position sequence independently after that. This network is applied separately and identically to each token position, which means it doesn't mix information between tokens. That is handled by the attention. And this fully connected network helps to model the complex nonlinear transformation of the token because it has a nonlinear. This improving the model's ability to capture deeper patterns. So this feed-forward neural network will change. In each transformer block, this FFN is combined with the residual connection and layer normalization to ensure the stable and efficient. So as a whole, this is the feed-forward. So in summary, in this lecture, we basically understand the transformer architecture. There is few things we have discussed, namely input embedding, positional encoding, multi-head attention, layer normalization, feed-forward neural. And in decoder architecture, we use the Markov architecture. Next lecture, we start large language models. Thank you very much.